we're dealing with continuity, we have to ask ourselves, where, if I was to graph this, would I have to lift my pencil? So continuities, they come in three different types. We narrow it down to two, basically removable and non-removable. Let me give you a quick rundown though. There could be holes, graphing something and open circle, that's a hole. There could be a jump, so closed circle there and open circle there. That often happens with piecewise functions, or it could happen if you have an asymptote kind of looking like that. Or it could be a gap, which would be an open circle, but that particular point has been redefined somewhere else. So there's holes, jumps, and gaps. I broke them up a little bit. However, this guy right here, this guy would be non-removable. Just erase the asymptote, we'll put it again. That would be non-removable. And this would be removable. And this would also be removable. If I was to graph something and it looked like that, then it would be removable because I can very easily figure out what goes right there. I can very easily fix it, so it's a removable discontinuity. Again, this one's removable because I can very easily fix it. I can just tell that point to go on down there and sure, it's fixed. These are a little bit harder. Those are non-removable discontinuities. Okay, so looking at the first problem in this section, we need to decide what values of x would cause me to lift my pencil when I graphed it. And you know, when you look at this long enough, you'll realize that this thing is continuous everywhere. I could graph it, if I had enough pencil lead, I could graph it from negative infinity to infinity and never have to lift my pencil. And so this one is continuous everywhere, sometimes dyslexically written as everywhere continuous. Everywhere continuous. Some people will write it as continuous from negative infinity to infinity. They'll put it like that. Either one of those is okay with me. Turning those words around sounds better, but that's up to you too. Okay, this one's a little trickier though. We need to know where this function does not exist, where I would have to lift my pencil. Let me say, instead of saying where it doesn't exist, I would say where I have to lift my pencil, or where there would be some sort of discontinuity if I was to graph it. Always looking at the denominator to see where that denominator would be 0, and I believe you'll know how to factor this. So this would be x plus 2 and x minus 2. Okay, so there are two places where the denominator equals 0, and because there are two places where the denominator equals 0, we're going to have two discontinuities. If I could kind of pause this problem right here and give you another hint. Anytime you have a piecewise function, one of the most obvious places to look is where the piecewise function would be potentially broken. You've got this piecewise function here, and you might have that, and you might have that. One is a, not definite, but a potential place for a discontinuity, because if you graphed it, you might would have had to lift your pencil at 1. Okay, just throwing that out there. I hope you caught what I threw at you. Okay, back to this problem. We know we have two discontinuities. One of them comes from where this piece would make, this factor would make the denominator equal 0. So x equals negative 2. Another one would be x equals positive 2. Well, that's great, but we don't know if they're removable or not. In the process of graphing this, if we were to graph it, and you can type it in your calculator and graph it if you like, and that will give you a great indication. Let me correct one easy error right there. If you type it in your calculator, put parentheses. But if we were to graph it in the calculator, we would notice an asymptote here and not here. Let me explain why. First of all, there would not be an asymptote here based on this. When you cancel out factors on the top and bottom, then the factor, the discontinuity, the point of discontinuity that corresponds to that you canceled would have been a hole in the graph. And anytime we have a hole in the graph, remember when we drew this a minute ago, there was a hole in the graph? That would be removable. When we graph this point, well, actually we can't graph that point. There is going to be an asymptote there. Because there's an asymptote, it's going to wind up looking like this, possibly, and that would make it non-removable. Okay, so if we were to graph it, we would have an asymptote here and a hole here. So somewhere along in this area we would have very rough sketch of the way it could potentially look.